Then next, I'm going to talk about very basic things about machine learning, the very basic overview of this whole course. Right? So what is machine learning? So a popular definition of machine learning is this is actually a program that learns from experience of E with respect to some class of task T and the performance of measure of P. And if its performance at task T as measured by the P improve the experience of E. So it's kind of like complicated. But one type of machine learning, particularly for the supervised learning, which is something that we can talk about this, is you can think about this as a driving by looking at the rear view mirror. That means you gain something from the previous histories, that you learn that you make predictions for the futures. So this sounds scary, but turns out it's been working very well in the past. Okay, so this is scikit-learn cheat sheet for this machine learning. So here's the starting point. So you can see in general, machine learning has been divided into 4 portions, right? So the first portion is the regressions. The second portion is classifications. In particular, if I draw a line here, so this is supervised learning. Then the next two right here, this is clustering and the dimension reductions. So for these two, this is unsupervised learning. Okay. So what is the difference between the supervised learning or unsupervised learning is because of this whole thing, right? So whether you have a label data, if you don't have the label data, it's usually unsupervised learning. If it is has label data, it's most likely it will be supervised learning. We will talk about this in detail in the later on. All right, so and this is whole roadmap of your machine learning if you are interested in all these kind of things. In fact, we are going to talk about almost everything here. We'll talk about naive Bayesians. We're going to talk about linear SVM. We have talked about k-nearest neighbors. And I'm going to talk about kernel methods, and SGD classifiers. We're going to talk about the lasso, elastic net, ridge regressions, and a lot of things, right? So for this one, clustering, we're going to talk about Gaussian mixtures. We'll talk about k-means. And we're going to talk about for dimension reduction, we're going to talk about PCAs, and also the most important part, the neural networks. So this is also a very big topic. So so in this whole course, it's being separated into 3 modules. So the module 1, that will be just purely on the supervised learnings. Unsupervised learning, that will be on module 2. I specifically separate the neural network, which is deep learning part, on the module 3. Okay, so these are the 3 things that we're going to talk about in the whole courses. So, and you are going to understand and the mathematical and what is the and the math of all these methods models. So, and you are going to implement it from scratch. So, and the key here and I already talked about this right here. But the key of this whole course is you are going to implement all these algorithms and models from scratch. So what does that actually means? I believe in 502 you already learned all these models like roughly. You talk about like regressions, like enriched regressions, SVM, and so on. But you only have just a quick understanding of what is going on here, and you're probably using scikit-learn and packages to actually implement this just with 1 or 2 lines. But the issue is you probably don't understand what is going on here. So for this courses, which is machine learning, that for the most part you are not allowed to use scikit-learn. So this is the key. You are not allowed to use scikit-learn unless there's some functions that I specifically let you to use. And if you want to implement some algorithm, for example, like Lasso, like say, and the logistic regressions, you have to implement from scratch. That means you only can using NumPy and SciPy. So this is something that is very different. Will be quite significant in for this courses. So that's why it makes whole courses very challenging. Because now you actually have to dive deep and unwrap all these black boxes, models, and algorithms to actually make sure you understand everything. All right, so we have a talk about this. So there are basically 3 machine learning paradigm. One is supervised learning. The second one is unsupervised learning. The third one I didn't mention about this, which is reinforced learning, will not be covered in this class. So for the supervised learning, so the whole idea is we have a label data. And the major differences between supervised learning and unsupervised learning is whether we have a labels. Okay. And also, if we have a label, we can have a direct feedback. That means, did I got it right? Right. So and what is the error? And for those and the part. And for unsupervised learning, there's no feedback. So and basically we don't know whether I'm right or wrong. So this is very important. And also for the supervised learning, we can make and predict the futures and outcomes. Basically, we can predict how accurate and how good it is. So basically, we can talk about accuracies, like and a lot of other metrics that you'll be interested in. And also here, right here, for unsupervised learning, the key is to find hidden structures, right? So there's some structures of the data. We don't know the label yet, but we want to understand the structure of the data just by looking at the features. So that's why it's basically the main topics that we will be interested in. So for this machine learning courses, I would say I would spend the most of time, like 2/3 of time on the supervised learning, 1/3 of time on the unsupervised learning. So this is basically, you can think about like neural network part is also a part of the supervised learning. So with the different data, we are going to and separate all these supervised learning, unsupervised learnings into into 4 classes. Right, so one is classification, one is regression, one is clustering, one is dimension reductions. I'm going to give you a quick overview of these 4 topics of what we are trying to do here. So first thing, what is the supervised learning? So this is a big pictures of the supervised learning. So the data that we have is we have a training data, we have a labels. You choose your own machine learning algorithm. Could be k-nearest neighbor, it could be logistic regressions. You build your own predictive models. Okay, so this is a training data. So you build models right here. Then you're going to give another new set of data. So this is usually called testing data set. Then you're going to make predictions for the testing data set. Okay, so this is the whole idea of the supervised learning. I mean, the whole supervised learning, almost all, I mean, every time it will be fall into these categories. Okay, so the basic setup of this supervised learning is we actually want to learn a function of f. So this is my training data D, which is I have the feature of x of I. So this is my feature. This is my target. Right, so this is my target. Or label. Sometimes we call it label. And sometimes we don't call it a feature, we call input, which is the same thing. Right, so this xi is the feature, yi is the target. So the whole point is we want to learn a function of f such that we can build a model of yi is equal to fxi plus some noise of epsilons. And in some senses, we want this epsilon as small as possible. In some kind of metric. We will, talk about that in detail later. If you have a new data of x, that is a new testing data set, that we can make a prediction of y equal to fx. Right, so this is, but this epsilon right here, you can think about as a training error. Right, so this is basically, a deviation from the prediction of fxi versus the ground truth of yi. So this is basically the training error, but this is not precisely the training error. And we need to and quantify this in a proper way for the training error as well. And of course, this f in general is very complicated. So what we can do is we can parameterize these functions. So we can do like parametric and parametric function approximations. So what we do is we can like parameterize these mappings into a family of functions. So basically this is actually, and you can think about it this way, this is fx theta. Theta is the parameter. So you can think about we have a family of the kind of functions, and we have this y equal to fx theta right here. Theta here is my model parameter that we need to be determinant. And also and it differs with the performances of the learning. So this is something like to be learned or to be trained. So the key is we want to find out the best theta. Actually, if we plug in the theta, then we can determine the functions of f, then such that it can can make the best predictions possible. All right, so and also, as I said, this whole thing has 2 steps. One is the training. So the step is, first step is training. The second step is the predictions. So the whole idea is we want to find the optimal theta star with certain of algorithms, which, it's likely to build an optimization problems. Build an optimization problems. And actually using these optimization algorithms to find the optimal theta star. And such that in some senses, for those training data that we have, we want our just the predictions of xxi theta star to be as close as yi in some senses. Okay, so I want these things to be close to the ground truth, such that I'm finding the right optimal theta star, and this f and the yi are as close as possible. And for the predictions, so this is very important. Once we find out the best theta star, and then we have a new data, then we can make the predictions for that. So this is basically prediction. So you can think about right here is the training. And right here is the prediction. So this is the two steps that is not avoidable for the supervised learning part. Okay, so so you can see from here, it's quite easy to do any kind of predictions. And once we have a good knowledge of theta, all we need to do is just plug in, and it can make the predictions. So the difficulty part is lies in that kind of training here. So the training is we actually want to train this f x theta on this training data set D. We have a talk about this. Say we have a lot of data, which is from 1 to n. And in general, this n could be very large in machine learning problems, could be tens of thousands of the data point. In fact, in the homework, you're going to work with a very large data set. So that's why I would suggest you to start your homework early so that you can have enough time to work on that. So basically, and the whole idea of, the performances of how to find the good thetas lies in how can we measure how close are these twos. So this is my predictions. This is my ground truth. I want to measure how good of this approximation by some loss functions. So basically, I'm going to create a loss functions, which is L of my predictions of my training data versus my ground truth. So this is my loss functions. So you can think about, in short, it can be written as just L, F, and Y. So it has to satisfy certain properties. That means if these two are close, then this loss should goes to 0. So this is very simple. Just think about something that is, F is close to Y, which is, that means my prediction is very close to my ground truth. And then this should goes to 0. So a very natural way of doing so is just a square loss. Basically, we subtract that and square the values. Okay, so this is a very commonly used loss functions. But of course, this is not the only one, as many other loss functions. We're going to talk about various different choices of loss functions. throughout this whole, courses. Then we need to minimize, but I want to emphasize this is just for one data point. So this is just one data point of xi and yi. But we have x1, y1 to xn, yn. We have n of that. So that means we're going to sum this loss together, take the average, and then this will be my total loss. So this is the average loss over my whole data set. So basically, we're going to sum all these data set and the loss together. And for I from 1 to the n, and divided by n. So this is average loss functions. So then we want to minimize this theta, and we want to minimize this loss functions with respect to theta. So this actually becomes an optimization problem. So that's why you need to take optimization before you're taking machine learning, because in very large portion of machine learning, it's optimization. So you're going to see these kind of optimization again and again and again. So that's why you need to have some background of the optimization. And also, if this loss function is just precisely equal to 0, that means for each component, it has to be 0. And I also want to emphasize another property is this loss should strictly bigger or equal than 0, right? It doesn't make any sense we have a negative loss. Loss is always bigger or equal than 0. So if you got the 0 loss, that means my predictions for the training data set is all accurate. So that means it's all perfectly accurate. In general, this is not possible. That's just being some very ideal cases. But just to let you know, if that actually happens, that implies I have a perfect predictions for my training data set. Okay. And I want to remind you, we have four topics: classifications, regressions, clustering, and dimension reductions. Right. So this is something I want to give a tiny bit introduction here. So regressions is usually what we talk about my label or target is actually a continuous variable. This is mostly covered in an applied statistics courses and practical machine learning courses. We are going to, I think, cover 2 or 3 weeks of the lectures here. So basically, this is kind of data that you see. So you can see this is my x is continuous, my y is also continuous, right? It's fairly straightforward. We can draw a line like this, right? So this is something. If you just use an eyeball, that's the line that you probably would drive, and predict. So this is very clear. You can using a polynomial to predict this data set. It's very simple. You can see it could be just a cubic functions, right? It could be a cubic functions. So what you can do is your theta could be just being, and your f is just could be, and your f is just could be like this, being theta 3 of x to the third, x2, x1, and x0. So basically your theta is nothing but just theta 3, theta 2, theta 1, theta 0. So we want to find out the optimal theta, which is and corresponding to the coefficients of this cubic polynomials. Okay, and this is my predictions right here. So my epsilon I is basically the deviation from my prediction. So this is usually considered as an error here. So there are a lot of things involved on the regressions. There's a lot of testings and some knowledge with that. It's basically being taught in the 565, but usually, in the perspective of traditional statistics, we usually focus on a couple very, very small data set, a couple hundred, couple thousands. That turns out these kind of statistics will be very important. You need to tell what kind of result we're getting here, whether my result is reliable, and can we improve that. But in the perspective of machine learning, these kind of things is getting not that important and gradually, because what we are dealing with millions of and tens of millions of data sets. With that big data set and all sorts of testing and statistics could be extremely difficult to do, because this data is just so big. It's very difficult to do any kind of realistic analysis other than you just make some prediction for that. So in the perspective of engineering and the realistic cases, if you're working with tens of millions data sets, that kind of statistics is no longer very, very important. But we are going to talk about in a little bit how to tell whether your model is reliable or not, because sometimes it will not. Okay, so that's good. And the classification. If yi, which is my target, is a discrete variable, or just for example, a y and a 0. So this is mostly covered in for this courses. We're going to spend a significant amount of courses, time for this classification. But this will also be covered in the applied statistics as well, and also practical machine learning. So if you took Mike and the 593, you are going to go through everything one more time, but this time you are going to only using packages, but you are going to work with a really, really large data set, right? So there are more skill sets. You have to clean the data and other things that you need to worry about that. So I mentioned I'm a little bit on in the 593 and 593 here. I'm also teaching 593 as well. If you're interested, you can take that as well. In 593, the most important thing is how you clean the data, how you understand the data, and how do you propose the right model for that. So this is the most important part. You need to understand the data so that you can get a good model for this. Otherwise, you are, doing garbage in, garbage out. You are not sure and what kind of models you won't be sure whether you are getting the right models or not. So, and for the classification problem, for example, this is a very typical classification problem. So we have a plus sign and a minus sign. So basically, we draw a line right here that to say, and to my left, this is minus. To my right, this is plus. Right. So this line perfectly separate these and a plus sign and a minus sign. And here we are just having the 2D data, just R2, right? So and my feature X is in R2. And my Y is just plus and minus. Right? So it's just 0 or 1 if you think about this one, or plus 1 or minus 1. All right. Right here, this is another data set that we have been using. We will use this data set a lot, which is MNIST data set. So what is MNIST data set? So we know this is 0, this is 1, and we have a 9. So basically we have a 10 categories, right? So 0 to 9. So this is very important. You have some idea of some data set we're going to be using. So basically, if you see this image, okay, this is 0. And you see this image, this is 9. So we have 10 class of and classification problems need to be solved. All right, so this is obviously not super easy. All right, so next. There are many problems and many algorithms that we can work with. But also in these problems, we have talked about some like testing and generalization. This is also very important. So I want to emphasize with one simple examples right here. For example, if we have this kind of situation, we have these data and so on. There are two possibilities that you can do. One is you can just draw a straight line like this, right? Like the purple one. Or what you can do is you can draw a high degree of polynomial such that it can like go through every point right here to make sure the training error is 0. So this training error is 0. But this one is not 0 because this is a nonlinear and it's just a linear straight lines. But the difference is if I giving a new data right here, this one has low training data, training error. Turns out has a high prediction error. Compared to the linear models. The linear model only have tiny prediction error. How come my more complicated models give a high prediction errors, but my simple linear regressions give me low prediction errors or testing errors? Why? I mean, is it true that the model is more complicated, then the performance is always better? So this is something that it's always important when we build models for machine learning. So and also same thing that can happen for the classification. So basically, this is two possible cases for the classification. You can either draw a line like this, which is quite smooth, or you can try to draw a highly complicated lines to perfectly separate blue and yellows, and blue and red. So which line is better? Which one is better? The more complicated curve, or just a smooth curve, right? So this actually has something to do with testing and validations. So basically, you need to examine the performance of this optimal fx theta on new set of the labeled data. You cannot just using training error. Training error is only to train, it is only to find optimal theta star. It doesn't mean the function that you learn is the one that you want. I moved this materials was previously covered in 595, and 565. It's all moved in 592. So this is something that we're going to spend quite a bit of time. I think 1 or 2 weeks of materials. So why this is important? I want my trained models can generalize to new data, right? So because I don't care my models works well on the training data. The most important things I care is I want my models to work well on those new data, which is testing data set. So what you can do here, which is a common practice here, it's always to make your data, say this is your data that you have. You're going to split the data into two parts. One is the training. One is either something called testing or validations. So So basically, usually it's like 80%. This is 20%. Right, so you actually have to manually split this data set into training set, all the validation testing data set. So what you do is you train your models on this 80% of training data set and evaluating the test errors for this validation data set, because the way you do is this 20% data set is never being seen during the training process, such that this 20% and the validation data set give you a good idea what kind of error that it will have if you have a new set of label data. So this actually is much more important to talk and to work and to evaluate this testing error, because the ultimate goal here is we want to minimize the testing error, not the training error. The training error is just purely finding out the theta star, right? That doesn't mean this model will generalize well for the new data. This is a completely different story. And also sometimes there are degree of freedoms that we can work with. For example, even with this regression problem right here, and what kind of degree of polynomial that we should be choosing? Should we choosing the linear? Should we choosing quadratic? Should we choosing the cubic? So that means the number of the model parameter also matters. If I change my model, numbers of model parameters, then theta star obviously will be different. So, and what we can do here is we can do some cross validations. We're going to talk about this in detail later of this whole courses, to actually to say how can we find out the best number of the model parameters for for generalizations on this validation data set. So we're using this validation data set to find out the optimal numbers of the model parameters. There are two situations that you will find that is very commonly find out. One is the overfitting here. The overfitting is exactly this red line here, which is trained very well on the training data set, but cannot generalize well on the new data set. So what is happening is it's caused by more parameters that needed. And you can see right here, we don't actually need that complicated polynomial right here. We're probably just using, like linear regression, that would be okay. So that's why it's trains very well, but generalized very badly. So this is a region of the overfittings. So so you see those kind of complicated curves, that's likely to be overfitted. And also we have a underfitting. So that means you will find out the training and the testing or validation error both are very low. So both are very bad. So this is and some like region, that means we need to make our model more complicated. So if it is like, that means my model is too simple for that problems. So this is basically a graph that we have been using a lot. So basically you can see this is actually, this is validation or testing error, depends what and how we call this. If my number of the parameter is increases, my training error always decreases with the number of the parameter. So that means if my number of parameter increases, my model is getting more and more complicated. But the issue is this validation error or testing error will first start to decrease, then will start to increases. So this actually gives us some idea that we can have this U shape of this validation error. So we have a like minimum right here. So this is the sweet spot of this number of parameters that we should be using, because over here, this is the region of overfitting. And over here, this is the region of underfittings. Right, so this is something that is very important. We have a like sweet spot of number of the parameter right here that actually split the underfitting and overfittings. If you make the problems more complicated than the sweet spot, that will be overfittings, and everything below that, that will be underfittings. So there are like some other like non-parametric set and the learning ways. We have a k-nearest neighbors, we have deep learnings. We're going to talk about this later on this courses. But rule of thumb is there's no free lunch. So that means there's no single best models that work perfectly for all kind of problems. So that means even with the simplest possible method like linear regressions, there are some data set that can work out very well. I mean, some data set, even with the like deep learning, no matter how you tune and how much complicated that you tune, it won't work very well. So I mean, it actually depends on the data. Some data works, some data doesn't work. So this is something called no free lunch theorems. The best way is to pick the suitable models based on the domain knowledge that you have and the trial and error. So basically, for this whole courses right here, I basically tells you what kind of model that you should be using. However, in 593, you just have the data. So you have to clean the data, you have to pre-processing the data, you have to actually find the best models to work with. So this is more like an engineering problems. Okay. All right. So unsupervised learning. So this is obviously and also very important part. So this is basically covered in 592, but it's also covered in my topic courses and also 585 practical TDA. The whole idea is you want to group the data in a way that belongs to the same group or the same cluster, are quite similar to each other's. Then others and then others so there are other clusters. So this unsupervised learning things, the whole idea is just to find previous unknown patterns without using any pre-existing labels. If you only have the data, for example, right here, you don't have the data and you don't have the labels at all. And we only have the points on the R2. So every point is on R2 right here again. So we don't have the labels, but like we can build a cluster, say I have a cluster right here, I have a cluster right here, I have a cluster right here. If we can build that kind of cluster, we can actually assign the labels to each cluster. So for example, this is cluster 1, this is cluster 2, and this is cluster 3. So basically we can automatically assign the label to each of the point right here. So clustering is automatically a labeling problems. But this labeling problems, that means I want to group the data is more similar to one clusters from here. But previous data that we have has no like clusters and has no label information at all. So this is basically clustering. Dimension reductions. So this is again is partially covered for this courses. We have another like topic courses on the dimension reductions. It's mostly basically to do manifold learning techniques, and also in like practical TDA classes, we are and we cover some of the materials as well. And for example, if this is my data right here, so you can see it's like very like skewed right here. So you can see this direction is very important because most of my data is being spread out in these directions. So technically, you can think about this, my data is 1D, right? Because everything beyond this, like any deviation, is you can consider as a noise. So this is actually a noise. So this is like deviations right here. Deviations right here. This is actually called principal component analysis. We're going to talk about in this courses. We're going to spend quite a significant time to derive everything that we need. There are other dimension reduction, for example, some manifold learning. So this is a typical something called isomap. Unfortunately, I'm not going to talk about this for this course's sense, but you can see this actually map like data on like R3 into R2. So this is Swiss row data set. So this is a plane. So this is basically using isomap techniques to unroll the Swiss row becomes like plane right here. Okay, so this is basically a simple overview of this whole course. And in the next part, we're going to talk and start to like review some of the knowledge of our prerequisites. So I have talked about these courses we require you know some like vector calculus, linear algebra, optimization, some programming. We will quickly overview these things. And so you have some good idea what we're handling right here. Okay, so that's all.